Hello everybody, welcome to CHEP Colloquium. Today we have Sarira Sahu from UNAM, Mexico City. Sarira did his PhD from IOP Bhubaneswar with SC Pathak, and then he was postdocs at PRL where I met him for the first time, and at Valencia, and then you were in Puerto Rico for some time, or no? No. Then he joined UNAM as a faculty member where he's a full professor now. And today he's talking about deciphering the TeV afterglow from the long gamma ray burst GRB 22190A. Why no neutrinos are observed from it? Okay, over to you, Sarira, actually.
Okay. Good afternoon, everybody, and let me thank Professor Sudhir and Professor Anand Narayan, to whom I know since long. Okay, so I will be talking on this So I will be talking on something that GRBs, which probably many of you don't know, because I believe most of you are working on high energy physics, so may not be knowing the terminology. So if you don't know, please ask me. So deciphering the TeV afterglow from the long gamma ray burst GRB 221009A, and this is supposed to be one of the biggest event in the astrophysics community. So they were expecting that they should see neutrino from this one, but they have not seen that. And then later on I will tell why no neutrinos were observed from this one. So this work was done in collaboration with my students. These two are students, and he is a professor in other university, and Subhash Rajput is a professor in California State University, Long Beach. And he is a particle physicist, but he told that he is interested to work in astroparticle physics, so he joined our group. Okay, so my talk is based on these two papers that I showed you, which we published exactly on the GRB 221009A. So this is my talk, the way I will go forward. So I will give a small introduction about the gamma ray burst. Then what is special about this gamma ray burst I will talk about. Since the observation of first gamma ray burst, they were expecting that because of its energy and intensity and all this, they were expecting that they should see very high energy gamma rays. By the way, very high energy gamma rays is above 100 GeVs, up to 100 TeVs. So this is the range. So they were expecting that they should see very high energy gamma rays, but they had not seen for decades until 2018, when they saw for the first time high energy gamma rays. So I'll talk about that one. Then I will talk about what are the most used model to explain the very high energy events. Then I will talk about the photohadronic model, which we have developed to explain the very high energy emission from high energy blazars, where we were extremely successful in explaining the spectra of very high energy emission from blazars. And there is a similarity between the mechanism which is operating in a blazar and a gamma ray burst. Then we thought that can be also applied to very high energy emission from gamma ray burst, and then we applied, which I will show you after the successful application of this model to that. Then we thought that GRB 221009A can be an ideal candidate to try there, and we also used there and explained that very well. But there is some peculiarity here that I will talk about, which is related to temporary extreme high energy BL Lac objects of temporary EHBL, which is a very special new class of objects nucleus of higher blazars, which are basically, well, when we saw for the first time, that time we had only seen one object, and recently it seems there are 2-3 more are there. So this is this is one of the rarest objects that we had seen, and this is related to that one which I will talk about, then summarize my talk. But in between, please ask me if you don't understand any terminology or anything. Maybe it is simple, but because you are never exposed to such type of terminology, you may not be knowing, so please ask me. Okay. Gamma ray burst normally comes in two ways. One is the long gamma ray burst, where 90% of the energy is released above 2 seconds, few seconds, maybe 100 seconds, below 100 seconds. And short gamma ray burst is 90% of the energy is released less than 2 seconds. And these are the, more or less, these are the percentage of what they see. Long gamma ray bursts are basically when a star, massive stars, collapses, and normally instead of going to a neutron star, it can go to black hole. So out of like approximately 1,000 this type of collapse, one of them can be a gamma ray burst. So this is a very special type of stellar collapse. Then short type of gamma ray bursts are basically, let's say, 2 neutron stars, they collide together, or neutron star black hole, they collide together to form a gamma ray burst, and which is, this is short type of. These are the type of gamma ray burst where people look for gravitational wave, because here the collapse is not symmetric, whereas here the collapse is symmetric. So here you don't see gamma ray, gravitational wave, but here probably you will see. Well, we have already seen that. Okay. Then the amount of energy released, you can see the scale that Sun produces 10 to the power 33 arc per second. This is the energy it releases. Nova is this much, supernova is this much. So you can see the scale. And now come to gamma ray burst. Gamma ray burst releases between 10 to the power 51 to 10 to the power 55 arc. And this gamma ray burst, well, again, the gamma ray burst, this means GRB 221009A means gamma ray burst GRB. 22 is the year 2022. 10 is the month October. 9th of October 2022 this was observed. And ABC they put if they see more than 1. Okay. And this is the amount of energy released. For the first time they saw such a tremendous amount of energy. You can calculate, scale this. So 22 order of magnitude more, and this is released in a few seconds. Yeah, this is released in few seconds, whereas this is released in seconds. So this, you can see the trillions of suns. Well, somebody in math science asked me a question, how much energy is that? We don't even know. So I just made this number so that you can see this much of energy, which is around 7 solar mass, can be completely converted to energy in few seconds, or in terms of Earth, 2.3 million Earth in few seconds will be converted to energy. So that is the amount of energy released in few seconds from these objects. Now, gamma ray burst, they tell this is the amount of energy released, this much of amount of energy released in few seconds, but in the energy range between 100 kilo electron volt to 1 to 2 mega electron volt, not much. So this is the major amount of energy is released, and just once it is released, then it is gone. After that, whatever will come is called the afterglow. That is in the title of my talk that I have put afterglow, because up to whatever they tell gamma ray burst, the first release of energy in the 100 keV to 2 MeV, there is nothing much you can tell about high energy physics or high energy particles accelerations. That comes afterward, when the particles are being accelerated, and then they will produce the high energy particles, and subsequently these high energy particles, whether it is proton or electrons or whatever you tell, they will interact with the background photons or outside whatever material is there to produce these high energy photons. And this means it is seen that around 1 to 2 events are observed per day. So somewhere else in the universe there are formation of black holes, around 1 to 2 black holes or maybe more, because we are not seeing the whole universe. So there are formation of black holes in the universe every day. Okay. So so normally what happens is that this is the cartoon that you can see. So this is a collapse of a star, massive star. When it collapses to a black hole, so the matter which is accreting into the black hole, some of this matter can come out, which are in the jet forms. And this is the jet. When the GRB is formed, this is the jet which is coming. Well, you can see this one, but these are not continuous jet. They are basically like waves. They are coming, and here, from here to here, the photon density is so high, or optical depth is so high, that photon cannot release. Basically, it is a soup, you can tell. So once it comes somewhere else here, then the optical depth for the process is lower than 1, and this is the place where it releases, and this is the place where you see the gamma ray burst. Beyond that, this side, left side, you will not see anything. But beyond this one, then what happens is that this jet which is coming towards us, it is expanding and it is going with a ultra relativistic speed. Something like velocity of this jet will be something like 0.999 c, you can say that. So this is the one, actually this is the place where nature has produced such a powerful jet, that this is the place where matter can travel almost close to the velocity of light. Whereas if you see in AGN, the velocity can be 0.9 or 0.99 c. Here you can put 2-3 more 9. Okay, so this is the place, and this is the place where it is interesting, because the afterglow, where all these particles which are, charged particles, let's say protons or electrons, they are going here. This is the place where they will be accelerated, and once they are accelerated and hit some background photons or whatever, that is the place they will produce these high energy particles. So that is what I am going to talk about now. So the people were thinking that whether these gamma ray bursts are from our system, from our galaxies or somewhere else, but from the distribution you will see that they are isotropic, so they cannot be of galactic origin, they are cosmological. In fact, now they have much more. This is 2700 gamma ray bursts they had seen, but it is long ago. Now they have seen many thousands, so you can see their distribution is almost isotropic. Okay. Yeah. How long? There can be kiloparsec. Okay. What is so special about the gamma ray burst 221009A? If you see the coordinates, so this is the place where it was observed. So here we have the galaxies, so you can tell that behind the galaxies. It has a redshift of 0.151. So if you see the luminosity distance, it is something like 748 megaparsecs. I will show you the number, how many centimeters, because astrophysicists like to express all these things in terms of centimeter. And this was observed by all the detectors. Whatever is there in the space, whatever is there in the ground, this was observed by all. Okay. So this was observed by, first this was observed by gamma ray burst monitor GBM which is in the Fermi telescope. Then after that it was observed, and simultaneously it was observed by almost all the telescopes which are there. Okay, and Fermi telescope for the first time observed the highest energy photon from this object, which is around 100 GeVs. Okay, T0, that T0 which I put is the same T0, but here it is written this small letter. This T0 is the time when 90% of the gamma rays in the low energy limit between 100 keV to 2 MeV are seen. That is defined at T0. So whatever you see after that, that is what they tell. So 240 seconds after the observation of the gamma ray burst, this is what it is telling. Okay. Then, so this is the this is the distance or redshifts of the object. So you remember this one, this is what it is important. And the amount of energy they estimated is something around 1.2 times 10 to the power 55 arc, which is the highest so far. They have not seen such high energy emission from a gamma ray burst. And now you see this is the brightest long duration GRB, and arguably one of the nearest and possibly the most energetic GRB above all that. So this is something which is very spectacular about this one. They had never seen before. And another interesting thing is that this GRB produced a significant ionization of the Earth's lower ionosphere between 60 to 100 kilometers, and is the strongest ionization ever effect ever recorded from a GRB. So this is also important thing. So once you go to that one, then this is referred to as the brightest of all time boat event. And from the start, from all these numbers, they saw that such type of event can be observed in every 10,000 years. So probably, so this is why it is one of the rarest event, and this is why people are excited about this one and try to see what physics, new physics they can learn from this one. Okay. Now, thousands. I showed you that 2,704, but now they have seen, they see almost every day around 2, and they are seeing since 1970s. Okay. So normally what happens is that all these space-based telescopes like satellite-based, they see a flash between 100 keV to 2 MeVs, and then once they see, they inform to the community that at this particular coordinate I saw a gamma ray flash. So then they inform all the other telescopes depending on how serious they are or what type of observation they had. They will inform, and after maybe within half an hour or so, many telescopes will point to the directions. So normally all the telescopes except the one who sees fast will see afterglow, because the first flash is the glow, you can tell, and whatever you see after that is the afterglow. So the fellow who sees the glow inform others, and within half an hour or so they will point to that direction and see that. So whoever sees that, they will see the afterglow. No, they don't see the flash. But this was something very interesting. There is a telescope called LHAASO in Tibet, China. It is probably the best so far in very high energy gamma rays, and this telescope exactly at the same time was looking in that direction. So probably it was recording even before the flash came, it was looking in that directions. So it recorded the whole history of the emission from this object. So this has two detectors, one is WCDA and another is KM2A. So WCDA observed 64,000 high energy gamma rays in the range 200 GeVs to 7 TeV. Then KM2A, which is in the higher end, it observed 142 very high energy gamma rays in the range 3 TeV to 12.2 TeVs. So this is the first time they observed such a very high energy photons. In fact, when the Chinese wrote the first paper, I think it was in Science, they told that they had seen a photon of 18 TeVs. So now, so what is so peculiar about that one? So this one, observation of, let's say, forget about 18 TeV, after reanalysis they told that no, we are sorry, so the function was not fitting very well, so it can be between 12 to 13 TeVs. And that was observed between 230 seconds to 900 seconds. Now, observation of this unusually very high energy gamma rays by LHAASO is incomprehensible. Now, so what is that? Okay, normally what happens is that if the redshift is 0.15 or luminosity distance is 750 megaparsecs, which is around 10 to the power 27 centimeter. See, normally the high energy gamma rays which are coming from somewhere else, outside of our galaxies, they will have interaction with the background photon, not the cosmic microwave background photon, but the extragalactic background light, which is in the infrared to optical or little higher than that. Maybe I will show you that one here. Okay, no, I will show you later on. Okay, so then they will interact with that photons and produce E plus E minus pair. So if the object or the source is far away, then the probability that your high energy photons which are produced there and coming to Earth you will detect is practically zero, or this is very, probability is very low. So now you see here, if you plot the amount of highest energy photon you will see from a source, which is a function of redshifts, if you see, then the highest energy photon which you will see from a nearby galaxies, which is also a high energy blazar, is Markarian 421. So maximum you can see around 10 TeVs. Okay? Well, they have seen little bit. Suppose if you have error in modeling the background light, probably you can see, let's say, 15 TeV or 20 TeVs. But if you see the distance redshifts of this object, which is somewhere else here, then you are not supposed to see a photon above 1 TeV. But we have seen a photon of 12 TeVs. So now question is whether we don't know how the extragalactic background light is distributed. That is one thing. Or maybe something new is happening. Maybe there is a Lorentz invariance violations of the photon, that's why it is coming. Or people are also thinking that the photons can oscillate to axions in the presence of a magnetic field, and probably that will avoid this extragalactic background light, and that can reach. So there are many explanations, because if these photons are coming, then it shows that universe is much more transparent than what we see. So that can be in this way you can explain. But this one, well, it is not really broken, but what happens is that, see, you have to see, I will show you in some plots, when you take into account the correction of extragalactic background light, you will see some around 1 TeV energy, the curve falls little faster. Okay? So you see, this is probably around 1 TeV, you have that, and because of that one, and it is purely due to the extragalactic background light, where high energy photons interact with the low energy photons and produces E plus E minus pair. So basically what happens is that the survival probability of a high energy photon, when it is coming from a redshift G, let's say, which is a function, this is the optical depth, which is a function of both the G and the energy of the high energy photon. So, and this survival probability is exponential minus tau gamma gamma. So which is of the order of 10 to minus 4. That means what happens is that your flux will be depleted by a factor of 10 to the power minus 4 or so that it will be very difficult to observe these photons. Okay. Now, observation of very high energy gamma rays above 100 GeVs till 2017 none were observed, but in 2018 for the first time it was observed, this GRB 180720b, which was observed by the MAGIC telescope, which is in La Palma in Spain. So this was observed. Then 2019 it was another one was observed. This one was observed by the HAASO telescope, which is in Namibia, and there is another one in 2019 which I have I think in the next slides I have. Okay, so these are the three they are observed and they have published the data. Okay, good question. When this normally this extragalactic background light works when your high energy photons are basically above 100 to 200 GeVs. For low energy 2 MeV photons nothing happens, they will come. Okay, so that 10 to the power 55 arc, which is equivalent to 6.7 solar mass or 2.3 million earth mass, that was released, and that has nothing to do with this extragalactic background light, because extragalactic background light will not affect that. That will affect only when your photon is very high energy. I will, okay, maybe here you see this is above 100 GeVs, it is in TeV, so it is plotted above 100 GeVs and this is redshift. So below 100 GeVs these photons are not affected by the extragalactic background light, or you can tell that E plus E minus goes to gamma goes to E plus E minus will be practically zero when you are in this energy range for the yes. Okay. So the models which normally explain this are leptonic models. Leptonic models means what normally happens is, because these are violent process in the universe where all the charged particles, which are basically electrons and protons, are coming, their power law, e to the power minus alpha, let's say energy to the power minus alpha, their distribution. So these particles when they are coming, maybe it is there in the next slides. Okay, so there are models which explain, these are called leptonic, hydronic, or both leptonics and hydronics, which I am not going to explain much about that one, but I can tell normally. Okay, so normally what happens that when there is a GRB, you are producing these jets, so photons are going, and if you see their energy, the flux as a function of energy, you will see these two peaks. For GRBs these are complicated, so like this it is very difficult, but in a blazar you will see that these two peaks are very prominent, which I will show you later on. The first peak, which is coming around 10 to the power 14 to 10 to the power 17 Hertz, is the synchrotron peak. The synchrotron peaks comes because when an electron in a magnetic field in the jet is going, it will emit synchrotron photon, and some particular frequency it will have a peak, and taking that peak into account, well, so this is the peak which is coming, you can tell around 10 to the power 14 to 10 to the power 15 Hertz. So this is coming. So now what happens that, but you have a power law for the electron which is like this, power law for the electron. See, these low energy electrons in the magnetic field will produce this synchrotron peak, whereas these high energy electrons, what happens is that they will kick this photon out in the peak region, they will kick this photon out and they will produce a second peak. So they are called inverse Compton, or because they are from the same family, you can tell synchrotron self-Compton. So this is a SSC peak, and this is a synchrotron peak, which is generic to all these. Okay, this is there. Now coming to the photohadronic model, let me tell little bit about that one. So your high energy proton comes. Photohadronic, what we are telling is that a proton interacting with a photon. So this high energy proton is coming in the jet. It is afterglow, it is getting accelerated, and this accelerated proton will hit in the background photon which is there in the jet itself and produce pions. It can be pi plus or pi 0 or maybe multi-pion. So this pi 0 will decay to 2 photons, and this pi plus will decay to mu plus nu mu, and subsequently you will see this neutrinos and you will see these gammas. But this gamma, if this gamma is very high, then it will produce E plus E minus pair with the background photon. Then again this electron or positron in the magnetic field will produce the synchrotron photon. So all these will go until your energy of the particle is so low that nothing can happen to that one. So basically you can see that if this is producing like this, so you can see after some time you can see a distribution of photons basically which are lower energy, or probably even you can see the infrared photon, not infrared, maybe comparatively higher energy photons but much lower than these energies. Okay. On the other hand, so these are the, so basically these very high energy telescopes like HAASO, MAGIC, Veritas, then this LHAASO, they observe these high energy photons, and these neutrinos are, well, if you are lucky, it can be seen by neutrino telescopes like IceCube, KM3 net and all this. Okay. So basically what you see is that in the future, so it is planned that you will see this one, you will see this one, you will see low energy photons, and probably if it is a short gamma ray burst, then probably you will be able to see gravitational waves. So that is precisely the idea, is that you will see all multi-messenger astronomy, you will see all these things. But when, I don't know. Okay. So anyhow, so originally photohadronic model was developed to explain the very high energy spectra of high energy blazars, which are called EHBLs, and this was extremely successful. So I will just tell about this one. So before that I will tell what are blazars or EHBL. See, these are active galactic nuclei or AGN. You forget about all these things. I also don't know anything about this one. So you come to these sites. So BL Lac objects, blazars, then BL Lac and flat spectrum radio quasars. So this here also you see there are LBL, IBL, HBL, EHBL and UHBL. So these last two are new type of objects which are very, very recent. But these are low energy BL Lac object, intermediate energy BL Lac objects, high energy BL Lac objects, and these are the objects which produce really very high energy gamma rays, and the high energy gamma ray background in the universe is mainly coming from this one. So that's why these objects are very interesting to study, because as you saw from the photohadronic scenarios, if you are producing very high energy gamma rays, and if it is a hadronic process, you must produce neutrinos. There is no other way. So from the pion decay. So if you are seeing this, basically you should see neutrinos. Okay. Now this one, well, these are classified according to their synchrotron peak, which is well, okay, maybe here. Okay. These objects are classified according to their first peak. You see all the AGN in general, they have two peaks. Depending on the peak position, in the synchrotron peak positions, you can divide them, or you can classify them, whether it is a FSRQ, which is around 10 to the power 12 to 13 hertz. Then if this is a LBL, it is below 10 to the power 14. If it is a IBL, between 10 to the power 14 and 10 to the power 15. and if it is a HBL, it is between 10 to the power 15 to 10 to the power 17, and if it is a extreme HBL, it is above 10 to the power 17. UHBL they are telling, but they have not seen really any clear evidence of that one, is if this peak goes above 10 to the power 20. UHBL, sorry. Okay, so these are classified according to their fast peak position, synchrotron peak positions, and also you can see this can also shift little bit. Okay. Now, so what are blazars? If you see, suppose this is a galaxies and this is the jet it is producing, it is the counter jet. Now, for some reason, if you are here somewhere else, you are within the cone, then this is called blazars, because any fluctuation in the flux or anything you can be seen directly. In fact, it is observed that even there is a variation in the flux in 30 minutes, 50 minutes. Okay, so they have seen that, and that, so these are interesting. Blazars are interesting because you are within the cone. Okay, just to have an idea, if it is a blazar where the central black hole mass is something around 10 to the power 6 to 10 to the power 9 solar mass, and the size of this cone can be the size of our solar system. So this is a cone which is of this size. Okay, but for GRBs it will be much smaller. If you are somewhere else here, let's say it is called quasars, and if you are somewhere else here, it is a radio galaxy. So you can see if you are somewhere else here, then the variation and all these things you don't see much. You don't see very high energy emissions. Here probably you will see some, but here you can see very well. So that is why study of blazars is very important to know the extraction mechanism of energy from the central supermassive black hole, physical properties of the astrophysical jet, then acceleration of charged particle in the jet, and production of ultra high energy cosmic rays, very high energy neutrinos and gamma rays and all these things. And also, because these very high energy gamma rays are coming from there, and they will be attenuated by the background photons, so it is important to put a tighter constraint on the extragalactic background light from these observations. Okay, now, yes. Why? No, but if it is, but imagine that some photons they will not interact and come. So in that case, if your neutrino has a mass and it is 750 megaparsecs, probably your neutrino will come little later than the photon. Well, those who will interact, you forget about them. You are not interested to see those who are absorbed or those who are producing E plus E minus pair. Those who are coming here, that is what you are seeing. Your instrument will see the photons which are coming here. It will not see which are absorbed there. Well, I will tell you, that is the last part of my talk. Okay, but please ask. I think there are some papers people have done that. Okay, so I think I have already told about this one. Okay, the photohadronic scenarios. Okay, normally what happens is that you see, normally from a blazar you will see these two peaks. So this is, as we know, synchrotron peak, it is SSC peak. But sometimes what happens is that for some reason, unknown reason, this will produce a third peak. You see here, and this will produce this one. Or maybe it will produce somewhere else here, but it will produce a third peak. It is very difficult to explain that your electron is coming and the low energy electron, the power low energy electron in this region, let's say, they are producing this peak in the magnetic field. Then the high energy will produce this one. Then you can tell that, well, I have still higher energy electrons, the other one, then that will interact with this one and produce the third one. Well, you can do that, but the price you will pay is that you have to divide this into different zones. So if you divide this into different zones, let's say you have 10 parameters to explain this one, and if you extend that one, you need 20 parameters to explain that. So then that is not convenient. You can feed that, but you have to pay heavy price for that one. Okay, so then what we thought is that maybe photohadronic scenario is very important in this region. When you try to explain this one, this is not coming from the leptonic process, or it is not coming from the acceleration of electrons, but it is coming from the proton which are being accelerated in the jet. Another interesting thing is that if the electrons are very high energy and they are in a magnetic field, they are extremely crazy in losing the energy. So imagine that if you have an extremely high energy electron in this region, and that is going in a magnetic field, even if it is a small magnetic field of order 1 Gauss or even less than that, that electron will emit photons, synchrotron photon like crazy. Okay, so you may not be able to reach to very high energy, so that electron will hit the photon background and boost this one to higher energy. Okay, so that is why it is, you have to look for some process which are not efficient in losing energy, and in that case proton is the one, because proton, if you see the energy loss in the synchrotron photon by electron or by proton, if you see that the proton energy loss will be suppressed by a factor of 1 divided by mass of proton to the power 4. So practically it will not lose much energy by synchrotron photon. So this is the one has to see that the third peak is very difficult to explain using all these scenarios. So one has to think of something else beyond that. So that is where we saw that protons can be interacting with the background photon to produce that, and these protons are power law. These are the, so differential spectrum of the proton or electrons are power law. So this alpha, which is the spectral index, can be greater than equal to 2, but we don't know exactly what the value is. Okay, so now so this is the process we see. So normally when in the blazars your matter is accreting into the black hole, it will produce the jet and counter jet, and this jet, this is in a normal case, so you will see these two peaks. But suppose something happens and it is emitting a very high energy photons, or that is called flaring events. In that flaring events you will see the third peak, or this one, third one, which is above few hundred GeVs to TeVs. That case it is very difficult. So what we assume is that during that time there is an internal jet which is being developed, and it has a density much high, photon density much higher than the one which is outside. So in that case what happens is that, and the most important contribution coming from this is from this delta resonance region. Also you can see, if you see this, delta resonance has the highest peak, and after that if you don't have a resonance, but if you produce this one, their peaks are smaller. So you can tell that, in fact, yesterday or day before yesterday there is a paper where they claim is that this is the most significant contribution and rest are not so important. So here now if you want to have this process, then you have to calculate this process in the moving frame of the systems. In that case what happens is that proton energy and the background photon energy will satisfy this condition, which is, this is the redshifts, and this is the bulk Lorentz factors, or the Lorentz factor through which this jet is moving, and this is the Doppler factor. But for high energy blazars, because they are, you are sitting here somewhere else, so their gamma is almost equal to D, so you can take D, gamma is equal to D. And here what happens is that, because normally in a normal blazars you can calculate what is the photon density here. Here the photon density is very low, so this process is not an efficient process. 2, so that means if you want to explain this third peak using this one, and but only a single jet, what you have to do is that you have to really have a super Eddington luminosity of proton. That means what happens is that normally Eddington limit is defined when the matter is going out and the radiation pressure, so there is a balance of that one. That balance one normally is the one where how much matter is falling into this, and you will calculate from that. But if you want to explain with this one in a standard jet where there is no inner jet, what you need is that you increase the photon flux very high, and from there when you see the luminosity in proton will be 1 million times the Eddington luminosity, so which is not practical. So that is why normally astrophysicists, they don't consider that one. Whereas during the flaring event, if you see that there is an internal jet which is developed and it has a higher photon density, and that higher photon density can be expressed in terms of the known one. This is the one which is outside, this is the one which is inside, and in that case you can explain that. And simulation in gamma ray burst also, they have seen that during the gamma ray burst they have seen that the inner region is more denser. Okay, so these are the kinematical conditions that I was showing you. You can, whether you want proton, neutrino or photons, this is there. Now for gamma ray, for high energy blazars, we had seen that high energy protons which are going in the jet, they are interacting with the photon to produce the delta resonance, and subsequently the gamma rays from the pi zero decay, which explains this one very well. We saw that the protons which are going and hitting the background photons are in this region. These are in the MeV region, about let's say 2-3 MeV to much less than 100 MeV. So this is the region where the protons will go, hit this photon background, produce the delta resonance. Delta resonance decays to pi zero or pi plus, then pi zero decay will produce the photons, and now this has to be corrected by the extragalactic background light, the distance which you are coming, and from there you can explain that. So to sum up all this, you can see that the observed photon flux on Earth can be expressed like this. This is called the intrinsic flux, and this is the one which is coming from the extragalactic background light, which is the suppression factor comes because of this one. If there is nothing between Earth and the source, this is 0, this is 1, so basically you will see the intrinsic flux. But because of this one, your flux will be reduced. And for GRB 221009A, this was the major factor which was reducing this very much, and that is why people thought that it is not possible, but we have seen that, and to avoid these corrections they told that there may be some new physics. So that was what was told previously. Now, so the extragalactic background light is coming because you have the galaxies formation. Yes, I mean, it is well known because the energy which I am going to tell is not much, less than 200 TeVs. But if you have a energy much higher, I will show you that later on, much higher, then you have a problem. Okay, so see, this is CMB, and this is the region where your extragalactic background light is there. This is coming from the Big Bang, and this is coming from the formation of galaxies, stars. So this is the formation of galaxies and stars. They are producing this light, and this light is responsible for very high energy photons which are coming. They will interact with these photons and then produce E plus E minus pair, so that you will not be able to see that if the object is very far. Okay. Okay, so this is the same one which I am showing here, that this is the factor which is responsible for the depletion of the flux. Now, well, using that one, we try to explain. You see this Markarian 501, which is next to next. I mean, the nearest one is the Markarian 421, and next nearest one is the Markarian 501. So you can see this was the normal event. These are the flaring events, because you don't know this object, Markarian 501, Markarian 421, and one ES 1959 plus 650. Their next one is there. They are studied extremely well. Okay, and multi-wavelength, multi-telescopes, and years they have studied that. So they saw that this object is a high energy blazars whose synchrotron peak is between 10 to the power 15 to 10 to the power 17. It is somewhere else here. And this object also they have studied very well, and they know quite well, I mean 100%, that these objects are high energy blazars. So we used our photohadronic model to explain, look, this is our result, this is also our result. Then also this object we explain this one, this is our result, the black one. There is another one, so this is the year when it was flaring, and we could explain all these things. Whatever I am showing, our model has explained very well. Even other one also we have explained. Recently we have also showed that suppose you see a very high energy gamma rays from an object, but you don't know how far it is, or basically speaking, you don't know what is the redshifts of that one. Then you take that you have seen the spectrum, and then you try to fit this one with a unknown redshift, then you will see that you can give a constraint to the redshifts. In fact, this object, what we gave a tighter constraint than the observation. So what you see is that this model you can explain the high energy blazars very well, and the mechanism is protons are accelerated in the Z environment, and they are interacting with the background photons, and that is producing the delta resonance, and subsequently that decays to charge and neutral pions, and that from neutral pion you will get these photons. And remember that your observed spectrum has to be multiplied with this one because of the extragalactic background. And these are not easy things. Basically this is a special branch in this high energy blazars. People work on that one, then they will have developed different models to calculate the tau gamma, and you have to, so they will give you a table like a log table, so you have to use that one and to calculate the what is the contribution from here. Okay, so now so we wrote a paper in yes. Well, we have written a paper on that, TXS 0506 plus 056. We have given a conditions that what is the necessary condition for a blazar so that it can produce this 290 TeV neutrinos, very high energy neutrinos. What we told there is that this blazar has to be in a, let me finish this one and then I will tell, because something is here. So we wrote a paper in 2019, and we classified emission from around 52 or 42, I don't remember, high energy blazars. From there we saw that low emission state, again I will show you this one. This is a really only free parameters that we have. So we started from the beginning, this model we developed, and finally we got a very simple equation. Here the spectral index delta is basically it is sum of two spectral index. One which is coming from the proton, which is alpha. Another one is the beta, because beta is coming. Remember that proton is coming and hitting this background, and this is a power law. These actually all are power laws. Okay, so this is a power law. So when proton has a power law alpha, it is hitting a background with a power law beta, so the resultant will be a alpha plus beta. But if the proton is coming and hitting this background, let's say this is some gamma, but it is a falling one, so minus gamma, so it will be alpha minus gamma. So you have to see that. So if you take that into account, then we saw that for high energy blazars, we saw that most of the blazars are in a low emission state. Around 50% of the blazars emissions are in a low emission state, and delta is exactly 3. So you remember that was exponent was minus delta plus 3. So if it is a 3, delta is equal to 3, so minus 3 plus 3 cancels. So your emission is very constant. no change. It is just proportional to exponential minus tau gamma gamma. Then there is something between, this is 15%, so rest 35%, no? So high energy emissions are between 2.5 and 3, and very high emission states are between 2.5 and 2.6, which is very small. And you see this is, so what we have told, that delta has to be between 2.5 and 3, which is very strict, and it should not go beyond this one. So if that is the one, and we saw that around, let's say 50 objects we analyzed, and we saw exactly they were following this one. So that is where we gave a classification of this emission, blazar flaring emissions, and we see till today that all the high energy blazars, they respect that. In fact, after that paper we have written more than 15 papers where we saw that all they follow the same behavior. Okay? So then the similarity between blazars and GRBs, practically speaking, they are practically the same mechanism, but only thing is that the blazar has a mass of order 10 to 6 to 10 to 9 solar mass in the center of the galaxy is the black hole, whereas for a GRB the mass is around 30 to 40 solar mass. The blazar has a magnetic field of order 1 Gauss, and the bulk Lorentz factor, or the Lorentz factor through which the jet is moving, is around 0.9 C for AGN. But for GRBs this is 0.999, so the bulk Lorentz factors can be very high. Otherwise the mechanism is very similar, so one can really, if you know how to work with blazars, you can extend that to high GRBs, but only for high energy emissions, very high energy emission. So to extend that one, this GRB 190114C, we explained, this is our model, we explained very nicely. Then the other one which was published in Nature, these are the Nature results, so we are better than that one, so that also we explain very well. Then this is another one, GRB, this one which was published in Science. This is the dashed one is the Science result, and this is our result. So we could explain very well. Now once we explain, and these are the only GRBs observed in very high energy. In 2020 they told that they have observed, but so far they have not released the data. Maybe something interesting is there, so we don't know. So whatever so far observed in very high energy, we could explain very well using the photohadronic model. Now we are convinced that the photohadronic model is really working well, so we could try to explain this GRB. Now, so what we did is that we told that this, because they are telling you that this is a very small number, so this will reduce the flux, observed flux. So we saw that let us increase this manifolds. But remember that you cannot increase this manifold, because you have to see that in the high energy limit your total flux has to be much smaller than 10 to the power 55 or energy. From there you can calculate the flux. It has to be much smaller than, maybe less than 1% or so, it has to be that. So if you satisfy that, even if you increase this one, that is allowed. So we saw that let us do and try. So then we increased that one and try to see whether everything we are getting is still in their place or not. Okay. So LHAASO, this Chinese observatory, they observed these high energy events. They divided this into 5: peak, rising phase, peak phase, 3 phases they have put. So this is the timing they have seen. So they put this in this way. This was published in Science 2023. This is, you can see, this is up to 7 TeVs. This is from the first telescope WCDA, Water Cherenkov Detector. Okay. Then so this is their, these are data points, and it is difficult to see their results, but it is their result is here, probably some of this dashed red line, here you can see this. So there are dashed line also here you can see. So they use the leptonic scenarios to explain that, but we told that if the photohadronic scenario is working well for the blazars, and it should work also for the high energy observation from the gamma ray burst, it must work for this one. And the one we fitted with this one is the black line, blue line, solid line is our result. So it fits very well. But now you see, okay, now you see what delta we use. Delta is equal to 3.4 or 3.5. It is not below 3. If you use delta is equal to 3, that is the curve. So it doesn't fit well. Okay, so what we did basically is that we tried to fit with 3 maximum, but we could not fit. Then we thought that, okay, let us take delta as a free parameter to check really how much it can be. So this is the value it gave between around 3.5, let's say. Now, so then it is difficult to interpret, because then we are not consistent. So what we saw, 5 minutes, okay. So then, okay, so what we did is that when we saw that both the WCDA, which is between 200 GBs to 7 TVs, this is the open boxes or circles are from that, and the one which are colored one are above 3 TVs but below 13 TVs. So you can see this, our result fits very well, but the price you pay here is that delta is above 3. So what we saw is that, so you can see very clearly using different background photon models, we could explain very well. Okay, so here, okay, let me, so what we saw is that recently we observed a high energy blazars, which was a temporary high energy blazar, in the sense that it is a normal high energy blazar, but suddenly sometimes what happens is that it goes beyond 10 to the power 17 hertz. So it is a high energy blazar, but suddenly for some reason it crosses the limit and goes towards the extreme high energy limit, but after sometimes again it comes back. These are seen in 3 or 4 objects. So one of the objects we studied recently, this object, this is 1ES2344 plus 514, which has a redshift of 0.044. We saw that this object cannot be explained through this one, but somehow there is a gap between the normal one, whatever we are explaining through high energy blazars, and there is something which is beyond that. And that is beyond that is coming because it is a temporary event. When it is crossing the limit, its spectrums are very complicated. Here you see, if it is a normal high energy blazar Markarian 501, which is well known, you can explain using the photohadronic model very well. But if it is a temporary one, it is impossible. That is the one, it is the normal one, but it has its behavior is very complicated. These are 2 zones, so zone 1 and zone 2. So what we saw is that there are some objects which are becoming temporary EHBL. You can either use 2 zones or you can use a single zone. Here the zone 1 is a standard high energy blazars where your delta can be between 2.5 to 3, but this is the zone where your delta can be above 3 or below 4. So if that is the one, then you can explain this very well, and you can explain that very well, and that is what we showed here. So that is why we got delta is equal to 3.4, and you can explain that beautifully. Okay, so now coming to the neutrino sectors here, because you see the delta is 3.4 or 3.5, you see that when you see the photon spectrum, 3.4 means it is falling very fast. Okay, because it is falling very fast, the flux is falling very fast, and that flux is proportional to neutrino flux. You have neutrino flux is multiplied by 3 times 3.8. Okay, sorry, 3 by 8. So in that case, what you will see is that the delta is 3.4, which is causing that the flux will fall very fast. So there is no time for the particles to be accelerated. Now coming to your questions, that if you want to explain the 290 TeV neutrinos from GRB, this blazar TXS 0506 plus 056, you need that your flaring should be minimum 1 week continuously, no discontinuity. It has to be minimum 1 week. Magnetic field has to be order 1 Gauss, and what else? There is another condition. Okay, there is another condition that if that happens, then you can accelerate the proton to a energy which is 20 times of, let's say your neutrino energy 300 TeVs. So 6 PeVs, because you need a proton of 6 PeV so that it will produce a 300 TeV neutrinos. So you can accelerate a proton to 6 PeV under the condition that your emission has to be very high energy. That means delta has to be between 2.5 to 2.6, very narrow. It has to be for minimum 1 week, and magnetic field has to be of 1 order, 1 Gauss. Magnetic field you can have, there is no problem. But this emission in very high energy state for 1 week is a difficult thing. Most of the cases you don't see. What they do is that they can have for half an hour, then come down. Then after few minutes or hours or days, again they can have. So that is why probably you cannot see neutrinos from these objects, or maybe something more is there. So that is why when we calculated the neutrino flux, it is much below all the IceCube generation 2. So we told that you cannot see these neutrinos. And another thing is that probably the jet is opening very fast, so that when the jet is opening very fast, particle density in the medium is going fast, decreasing very fast, so that even if you are accelerating a proton, it doesn't have a background photon to hit, so that you cannot produce neutrinos of very high energies. Well, I think I have finished this. So, and there is another thing is that if you calculate what is the angle through which this jet is coming towards us is 0.3 degree. So that is another very narrow jet, energy is tremendously high, and as I told you, it is like one of the very high energy, extreme high energy blazar, which is temporary, which is the rarest. So the combination of 3 is making this the rarest event. That's why it is very difficult to see such events very frequently. Okay, thank you. No, because that you see them, so they are you are within the cool. Otherwise, GRBs are the objects, they are exactly like blazars. But you multiply with 1 million. That's all. Excuse me. How do the? Okay, inner jets. Well, that is what we proposed. Because if you don't have that, first thing is that theoretically, if you don't have a compact jet, but density is high, then you know that when a particle is going, if the target material is not very, thick, let's say, you don't have interactions. So either you have sent lot of protons with a lower density photons, or you send lower flux with less protons but higher density photons. But you cannot send proton, you can, because if you have more protons in the flux, then lot of energy will go to the proton, so that your jet, which is ultra relativistic, will be Newtonian. You cannot have that. So you cannot eject lot of protons. That is for sure. Now, if you don't have lot of photons, then practically you don't have this. Now, there is a group in Valencia, University of Valencia. They have done the simulations that when you do a cross section of this jet for a GRB, they see that inside they see a denser medium which is going. So if you think in that way, then you need a inner jet, and that is not always. That is only when you have a very high energy flaring events. If it is a normal event, that cone is perfectly okay. But if it is a high energy flaring events, maybe something is going, accretion is some different way of accretion is going, and it is producing a inner jet which is comparatively denser. So that is the one. So I mean, we wrote that fast, but after a few years I talked to some people from GRB group in Valencia, and they told me that they really see a inner portion which is much denser. There can be some difference, because there are other models, the multi-jets, they tell. Suppose your cone is like this, but there can be some deviation from that, and because of the deviation you will produce the multi-jets. But it can be, there can be a difference. But because if you see the kinematics of the jet, most preferably it will be in the same one, same direction. Okay. Maybe this question I can answer. Okay, sorry. Yeah. No, it is because of the jet itself. Okay, there will be matter, but that will be far away. But when it is coming as a jet with almost no interaction. Probably you might have seen in the astrophysics books, they will put a jet of kiloparsecs, just like that. Because practically speaking, there is nothing, so this jet can move kiloparsecs without any interactions. Thank you.